So welcome to lecture 2 on electric potential and capacitance. So previously we have seen the relation between the electric field and potential. We have defined potential and the potential difference between the 2 points, and have also seen the relation between the electric field and potential. Now we are applying the concept of potential to understand the potential due to an electric dipole. So let us begin to understand potential due to an electric dipole. So if we consider a dipole that is a negative charge and a positive charge separated by a small distance apart, which is equal to 2L in this particular case I am taking, and we are trying to calculate potential at a point P, which is a far away point and is at a distance r from the center of the dipole and is making an angle theta as shown. So now for evaluating this, let us draw the line joining this negative charge and the point P, and the positive charge and this point P, and we are saying that this distance is equal to r1 and this one is r2. So if we produce this line in the backward direction, which is the central line, and if we say that the dipole is very small in comparison to the distance r, so over here I can draw a perpendicular like this from the negative charge and a perpendicular like this from the positive charge, and if we name these points, so I am naming this one as A, this one is B, so we are calling this one as N, this one as M, and that one is point P. So over here we are saying that the distance 2L between the two charges is very small in comparison to the distance R. So if it is so, if I consider triangle OMA, where O is this central point, so if we select this triangle OMA, so we have this angle as theta and this distance is equal to L. So if we calculate OM from here, so we can say that OM can be calculated as L cos theta, and similarly ON is also equal to L cos theta. Now the another point which we can mention over here is that the distance R1 is equal to, which is equal to BP, can approximately written as equal to the distance NP, and this NP is equal to R plus L cos theta. So the distance OP was already R, we have added ON to it to make it R plus L cos theta, and similarly the distance R2, which is equal to AP, can be approximately written as equal to MP, which is equal to R minus of L cos theta. So these are the valid approximations which we are using, and again I am saying or repeating this statement maybe for the third or fourth time, that the distance 2L is smaller in comparison to the distance R, and hence we say that the potential at a point P, potential being a scalar quantity, will be given by the potential due to positive charge A and potential due to the negative charge B. So since the potential due to negative charge will be negative, we will subtract the two values of potential, and we can write this equation in this way, that the value of potential at a point P can be written as, so due to the positive charge it will be KQ, and the distance is R2, that is R minus L cos theta, and due to the negative charge it is KQ, and the distance is R plus L cos theta. So if we start evaluating this, we can say Vp is equal to KQ R plus L cos theta minus R plus L cos theta upon R square minus L square cos square theta. And we can write it as Vp is equal to twice of KQ L cos theta upon R square minus L square cos square theta. And since the value of dipole moment can be written as the value of dipole moment is equal to charge into separation between the charge, that is equal to 2L. So Q into 2L can be written as the value of dipole moment P. So we can write this expression in this way, that the value of potential at a point P can be written as Vp is equal to P cos theta or Kp cos theta, or we can put the value of K as 4 pi epsilon naught, and then there is a term R square. So we are ignoring L square cos square theta because L was very small in comparison to R. So we write it in this way, or we can not omit that expression and obtain this equation as well. So in case you are not taking approximation, you can use this expression, but for most of the purposes we are going to use this expression. So we obtain P cos theta upon 4 pi epsilon naught R square as the value of potential due to the electric dipole. So now let us take some notable points from this expression which we have deduced. So the first notable point from the expression which we have deduced can be used for calculating of potential on the axial line. So potential on the axial line. On the axial line. So we say that the axial line is representing that theta is equal to 0 degree. So if we substitute the value equal to 0 degree, so we will obtain the expression for potential as P cos 0 degree upon 4 pi epsilon naught, and we can use this expression L is R square minus L square cos square 0 degree. So the expression is going to be like P upon 4 pi epsilon naught R square minus L square, and if I ignore L square, then we can write it as P upon 4 pi epsilon naught R square. The next note which we can take is on the equatorial line. So if we take the potential on the equatorial line, so the potential on the equatorial line will be taken when we consider that theta is equal to 90 degree. So if we take theta equal to 90 degree, the expression P cos 90 will become 0, and hence we say that Vp is equal to 0. So the equatorial line of the dipole is going to be the equipotential plane where the potential is equal to 0. So let us discuss a numerical over here. So the figure shows a charge array known as an electrical quadrupole. For a point on the axis of the quadrupole, obtain the dependence of potential on R such that the R by A is greater than 1, and contrast your results with that due to an electric dipole and an electric monopole, that is a single charge. So if I draw the arrangement once again, so we are saying that there is a quadrupole and the quadrupole is drawn in this fashion, such that the separation between them is equal to A, and the charges at the points are plus Q, minus Q and plus Q respectively. So if we consider a quadruple, then it is looking like this, and the value of potential is axed on the axis of the quadruple. So we are considering that the value of potential is to be calculated at a distance r somewhere here, which we call as point P. So we are naming these points as x, y and z respectively. So now the electrostatic potential being a scalar quantity, so potential at the point P will be potential due to x, and potential due to charges at y, and potential due to charges at z. And hence we can write it as k q upon the distance, that is equal to r plus a, and since the charge is negative, so we take it as twice of kq, the distance which is equal to r, and plus kq upon the separation which is equal to r minus a. So if we solve this expression, so then we can write it as q upon 4 pi epsilon naught 1 upon r plus a minus 1 by r plus 1 upon r minus a, and this entire expression can be solved in this way. So we are taking 4 pi epsilon naught, and if we take the LCM over here as equal to r plus a and r minus a, so the expression which we are going to obtain over here is r minus a minus of, so over here there is 2, so twice of r plus a and r minus a, and then we will obtain r plus a. So this is the expression which we are going to obtain while writing potential at a point P. And on solving this expression, we obtain q upon 4 pi epsilon naught 2a square upon r square minus a square. So we will get something like this: q upon 4 pi epsilon naught 2a square upon r square minus a square. And this expression can further be approximated using the condition which is given in the problem. So we rewrite this expression as twice of q a square upon 4 pi epsilon naught 1 minus a square by r square. So we are approximating this in this way, and then we are left with the expression over here which is equal to 1 by r cube. So on this value I can say that the value of r by a is greater than 1. Now since r by a is greater than 1, So therefore A by R is less than 1. And hence we can write this expression as twice of Q A square upon 4 pi epsilon naught, and then we are left with 1 by RQ. Or we can say that this expression can be written as 2KQ A square upon RQ. Now from this expression which we have deduced, it can be inferred that the potential in this case, that is the quadruple, is inversely proportional to RQ. So for a quadruple, now for a dipole we have seen that the potential is inversely proportional to R square. So this one is for a dipole. And for a monopole, we say that potential is inversely proportional to R. So this is the inference which we are obtaining from the expressions of quadrupole, dipole and monopole respectively. Suppose this, let us deal with the work done in rotating an electric dipole in uniform electric field. So we are dealing with this small topic over here, where we are writing an expression for work done in rotating an electric dipole in a uniform electric field. So I am simply writing in a uniform E vector. So if we consider a dipole with a dipole moment, that is P vector is equal to twice of QL, such that the value of charge is Q and the separation between the charges is 2L, is rotated in a uniform electric field through an angle theta from its position of stable equilibrium, then the work done by the external agent in rotating the dipole further can be calculated in this way, that the work done dW can be written as tau d theta. So we are writing this expression where we are expressing it in terms of Pe sine theta d theta. And if we suppose that the integration is from 0 to theta, so we can say that the value of work done, that is W external, can be written as Pe 1 minus cos theta. So this is going to be the expression for the work done in rotating an electric dipole in a uniform electric field. So post discussing the value of electric potential due to a dipole and the value of potential due to a quadrupole, and contrasting our results with the electric dipole and electric monopole, let us understand electric potential energy. So now let us begin with the discussion of potential energy for the charge particle configuration. So we are considering a system of charge, and the charges of the system exert electric force on each other, and if the position of one or more charges is changed, then the work may be done by these electric forces. So we define the change in the electric potential energy of the system as the negative of the work done by the electric forces as the configuration of the system changes. So why we are doing so, or why we are saying so? So let us understand it this way, that there will be an external force which will be doing some work done, and there will be electric force which will be doing the work done, and that is contributing to change in kinetic energy according to the work energy theorem. So we are saying that the charge is taken slowly from one position to the another. So we are saying that the change in kinetic energy is equal to 0 in this process. and hence we can say that the work done by the external force is equal to negative of work done by the electric forces, and this work done by the external force is stored in the form of electric potential energy of the system. So now in order to understand this, we are considering a system of two charges Q1 and Q2. So we are considering the system of two charges Q1 and Q2, which is at position A and B respectively. So now what we are doing is we are saying that the charge Q1 is fixed and the charge Q2 is taken from a point B to the point C. So we are taking this charge from a point B to the point C somewhere here along this line ABC. So we are considering that the distance AB is equal to R1 and the distance AC is equal to R2. So we are considering that this distance as R1 AB as R1 and the distance AC as equal to R2. Now while the charge particle is displaced from B to C slowly, the force which is acting due to the electrostatic interaction is kq1 q2 by r square, and since the distance is not fixed, the value of this force is variable. So over here we are considering a small displacement of the charge q2 in which its distance from q1 changes from r to r plus dr. So we are considering a position of a distance r and the position is changing from r to r plus dr. So during this displacement we wish to write the equation of work done by this force in the small displacement dr, and we can say that the value of work done can be written as dw is equal to k q1 q2 upon r square dot dr. So the total work done by the charge Q2 while it is moving from B to C can be obtained if we integrate this expression from R1 to R2. So from here we obtain the expression for work done as K Q1 Q2, and integration of 1 by R square is minus 1 by R, and hence we obtain the expression as 1 by R1 minus 1 by R2. So now no work is done by the electric force on the charge Q1 as it is kept fixed. So the change in potential energy of the system, so I can say therefore the change in potential energy of the system, which can be written as U R2 minus U R1, can be written as negative of work done, which is equal to minus W, and we obtain this expression as U R2 minus U R1 as equal to K Q1 Q2 1 by R2 minus 1 by R1. So we choose the potential energy of the two charge system to be 0 when they have infinite separation. That means when they are separated by a very far distance apart, that is they are widely separated, so we say that potential at infinity is equal to 0. So the potential energy when the separation between them is R can be written as, so we can say that the potential energy when they are at a distance R can be written as UR is equal to potential energy at R minus potential energy at infinity. So that is over here we are intending to say that R1 approaches infinity and R2 is a certain separation R. So if we do this substitution in this expression over here, so we end up getting the value of potential energy as K Q1 Q2 upon R, which can be written as Q1 Q2 upon 4 pi epsilon naught r. So this equation is derived assuming that one of the charges is fixed and the other is displaced. So however, the potential energy depends essentially on the separation between the charges and is independent of the spatial location of the charged particles. So the expression of potential energy of the pair of charges is going to be the same irrespective of the fact what the two charges are doing. So now we discuss about the sign of potential energy. So over here, since two parameters are involved, that is two cases are involved, that the forces can be attractive or repulsive in nature. So we say that the potential energy for the system can be positive or negative. Potential energy for the system can be positive or negative depending upon the nature of force. So if we consider that the force is attractive in nature, if the force is attractive in nature, so we say that the potential energy is going to be negative. So for the same reason, we have taken the potential energy or the gravitational potential energy as negative, because the force between the two masses always used to be attractive in nature. So if you just remember, the potential energy due to the gravitational interaction between the two masses used to be minus g m1 m2 by r. And the second case is when the force is repulsive in nature, that is both the charges are positive or both the charges are negative. So the potential energy is going to be positive, that is plus k q1 q2 by r. So this must be very well kept in mind whenever we are solving any case, or whenever we are solving any system of charges and calculating the value of potential energy for it. So now if we consider that a particular charge system is having more than two charges, then what is going to be the potential energy due to this system? So we say that since potential energy is a scalar quantity, so we will add the potential energy due to the interaction between the each charge particle. So if we consider something like this, so we are taking a simple illustration. We are going to calculate the potential energy stored when this for this particular configuration, where the charges q1, q2 and q3 are placed on the vertices of an equilateral triangle. So we take this distance as r. So in order to consider this, so we try to rebuild this configuration. So when I say we are trying to rebuild this configuration, so I basically mean to say, so let us consider as if we are bringing all the charges from infinity. So when we bring the first charge from infinity, there was no charge present in space, and hence no energy or work is done against any external field. Now if we will be bringing another charge q2 from infinity, then due to the electric field produced by q1, there will be some work done, and hence the potential energy is stored, and I write the first one, that is u1, is equal to k q1 q2 upon r. Now if we think about getting the third charge particle from infinity, so we say as this third charge particle q3 comes in, so the electrostatic interaction will be between charge q1 and q3, and also between q2 and q3, and hence the potential energy while bringing the charge q3 can be written as k q1 q3 upon r plus k q2 q3 upon r, and hence over here I can say that the total potential energy of this system is equal to U1 plus Q2, which is equal to K upon R Q1 Q2 plus Q1 Q3 plus Q2 Q3. So this is going to be the total potential energy for this system of charge.